Goedemorgen, dames en heren, ladies and gentlemen, geachte collega's, dear colleagues. I hereby formally open the session and I welcome you all to the public defense of Mr. Dylan Bollen. Before we start, I would like to introduce the members of the exam committee. So from abroad, we have Professor Peter Tuthill from the University of Sydney, but he will not join today. He was there at the preliminary defense already. We have Professor Jonathan Ferreira from the Université Grenoble uit. We have Professor Henri Boffin from ESO. Then from the local university, we have Professor Johan Sundqvist and Professor Vistana, who will join online also. And then we have three promoters. We have Professor Ursula De Marco from Macquarie University, Dr. Devika Kamat, also from Macquarie University, and Professor Hans van Winkel from the Institute of Astronomy here in Europe. My name is Mieke de Kok, and I will act as the chair of the committee. Now, what will be going on? Mr. Dylan Bollen has presented to the faculty his PhD thesis on the topic jet creation in post-asymptotic giant branch biomass in partial fulfillment of the requirements for the degree of PhD in science, astronomy, and astrophysics. He shall now publicly defend his PhD thesis. Mr. Bollen, you are invited to give a presentation of about 45 minutes about your work, and afterwards, the exam committee will ask questions. We will thoroughly discuss the document. So I now give the word to you, Mr. Dylan.
Welcome everyone. Thank you for joining me today, either in person or online. I'm very excited that I can present to you the work that I've been doing these past 4 years, which has resulted in this thesis titled Jet Creation in Post-Asymptotic Giant Branch Binaries. Now, there are already quite a lot of components in this title, like jets, post-asymptotic giant branch, and binaries. So therefore, I will start today with explaining some basic concepts. And then after I've gone through those basic concepts, we'll highlight what we already know about these post-asymptotic giant branch systems. And then after that, I will go into my own work. But so first, let's begin with the beginning. What is a star? Well, if I would ask you to give me an example of a star, I assume that most of you would reply with our own sun. But what is our sun, and why does our sun shine light? Well, stars like our sun are, in the most simple terms, massive spheres of matter that are held together by their own gravity. And a star like our sun is so hot and has such a high pressure in its core that it can fuse chemical elements. One of the main fusion reactions that happens in stars is a fusion from hydrogen to helium. And so these fusion reactions, they release radiation, which is what we eventually see. So that's how we observe stars. But now, how are stars born? Well, all stars are born from large star-forming regions. So these regions will start to collapse under their own gravity, and they will form protostars. And once the pressure and the temperature in the core of these protostars are high enough, they will fuse hydrogen to helium. And so that's the moment when a star is born. Now, a star will remain stable for the majority of its life, so we'll just burn hydrogen into helium in its core. But what happens once that core runs out of hydrogen to burn? Well, the remainder of the star's evolution will mainly depend on how massive the star is. And here we are interested in this cycle, the cycle of low to intermediate mass stars. So these are stars with a mass less than 8 times the mass of our sun. And so once that core runs out of hydrogen, it will shrink. And meanwhile, those outer layers will be pushed outwards. And so the star will grow in size and becomes a red giant. After this, the star will be able to fuse other chemical elements, such as helium, for example. But eventually, all of this will stop as well. And now the star will blow away all of its outer layers until nothing remains but their bare core. And if those outer layers that have been blown away are still close enough to that hot central core, those outer layers can become ionized and will light up. And that will create one of these nice planetary nebulae. Now also this, now if we would take all of those stars, or all the stars in our night sky, and we would order them according to temperature, or color, and brightness, or luminosity, we would get this diagram. So this is what we astronomers call a Hertzsprung-Russell diagram. And in this diagram, you notice that most stars are on this line. This is called the main sequence, with cool and less massive stars on the bottom right, and the hot, massive stars on the top left. Our sun will be located here. And so throughout its evolution, the sun will move on this diagram, and it will move along a path that looks quite a lot like this white track. So at the moment, our sun is burning hydrogen in its core, fusing it into helium. Once this stops, the star will, or our sun will move up to become a red giant. After this, it will also become an asymptotic giant branch star. And eventually, it will cross this path. And this is what we call the post-asymptotic giant branch. So that's the phase that I'm interested in. After this phase, the star can become a planetary nebula, and it will end its life as a white dwarf. So what is a post-AGB star? Well, a post-AGB star is a low to intermediate mass star that is in its final phases of its evolution. And on this track, it might appear as if the post-AGB takes up a large part. But don't be mistaken, a star like our sun, for example, spends roughly 10 billion years on the main sequence, but it will only spend about 10,000 years on the post-AGB phase. So whilst 10,000 years might look like a long time for you and me, it is negligible in the lifetime of a star like our sun. So this shows that the post-AGB phase is really more of a transition phase from the giant phase to the white dwarf phase. And we astronomers, we like to look at the stars through telescopes. Also, KU Leuven has its very own telescope, the Mercator telescope, which is located in La Palma, one of the Canary Islands. And so with this telescope, we can observe stars using a technique called spectroscopy. So the basic concepts of spectroscopy are that you collect the light of a source, and you then split that light up in different wavelengths. So that's similar as when you send light through a prism. If you do this for optical light, you will get this rainbow of colors, or a spectrum of light. So now we can distinguish three main types of spectra. First, if you would observe a hot and dense source, and we would send that light through a prism, we would get this continuous spectrum with no real breaks or gaps. If you would observe a less dense cloud of gas, and we would send that light through a prism, we would get this. This is an emission line spectrum, where we have these fine bands with large gaps in between. And these lines contain a lot of information about that cloud of gas. Chemical elements, like hydrogen, for example, emit light only at specific wavelengths. So that means when we observe an object and we examine its emission spectrum, we can also determine what chemical elements are present in this cloud of gas. But now, what if we have hot, dense source, and in front of that a cloud of gas, and we observe that, send that light through a prism? We would get this absorption line spectrum. So we again have that continuous spectrum, but with these gaps in between, or these small lines, these black lines. These are absorption lines. This is caused because that continuous light from that hot dense source will be absorbed by this cloud of gas, but only at specific wavelengths, depending on which elements are present in that cloud. So if we would apply this technique to our sun, we would get a spectrum that looks like this, an absorption line spectrum. But why is it that when we observe the sun, we get an absorption line spectrum. But also in the sun, we observe two layers. The innermost region that we can observe would give us this continuous spectrum. But around that, we have a second layer that is less dense and cooler. So that continuous light is absorbed at certain wavelengths, which eventually results in that absorption line spectrum. And as you might have noticed, there's a different method of representing this. So instead of looking at those colors with those bands, we can also easily determine the strengths at each wavelength. So also in my work, I look at spectra, but I don't look at spectra of our sun. I look at spectra from these post-HGB systems. And there we notice something interesting that happens. Those lines appear to periodically shift to the left and to the right. And this can be explained by that post-HGB star being part of a double star system or a binary. So we have two stars that are orbiting a common center of mass. Then that post-HGB star will always be moving towards us and away from us. And this is what causes this shift. So you can compare this with an ambulance. When an ambulance drives towards you, the sound waves will shorten and the sound will be higher pitched. When an ambulance drives away from you, the opposite happens and the sound becomes lower pitched. So this is the same with light from an object. When the post-HGB star moves towards us, the wavelength of the light will shorten and it will move to the blue. When it moves away from us, the wavelengths will lengthen and it will move to the red. So now we have these post-asymptotic giant branch systems from the title. So we have the post-HGB star, which is very bright, and a companion star, which we do not observe, but we know it's there because we know this system is a binary system. But that's not all. We also know that this system is surrounded by a disk of gas and dust. So this disk was created during earlier phases when this star was still an HGB star, and it still had a strong stellar wind, so it was losing a lot of mass. Now, because of the presence of that companion star, a lot of that mass is funneled onto the orbital plane, which then creates that circumbinary disk. And this disk has been observed in using interferometric techniques. So here you see a reconstructed image of one of these systems where the light from the post-HGB star has been removed. And what you see is this ring. And this ring corresponds to the inner disk ring of that circumbinary disk. And then we also know that there's a second disk present in these systems, a smaller accretion disk around the companion. Now, the mass from that accretion disk has to come from somewhere as well. And there are two possible sources that could feed the mass in this disk. The first possible source is a flow of matter from that circumbinary disk onto the companion. So we know that this flow exists because we have evidence in the chemical composition of the post-HGB star that such a flow must be present. So here on the right, what you see is not an actual observation, but it's a simulation of such a binary system with a circumbinary disk. And you also see these accretion flows where two smaller accretion disks are formed around the star. But as I said, there is a second possible source that could feed that accretion disk, and that is the post-HGB star itself. So when this star was still an HGB star, it had a very strong stellar wind. Now that wind is not that strong anymore, but it's still there. So this post-HGB star could still provide the mass to that accretion disk around the companion. And what we know as well is that a high velocity outflow or a jet is launched from the vicinity of that companion. So now we have these jets creating post-asymptotic giant branch binary systems or post-HGB binary systems. So there's one thing that I haven't touched upon yet, the jet. So what is a jet? Well, let's go back to the first ever description of a jet that was made by H.D. Curtis in 1918. And he described the a jet in a galaxy called Messier 87 or M87. And he described it as a curious straight ray, apparently connected with the nucleus by a thin line of matter. Now, that's already a simple but very accurate description of a jet. So a jet is a collimated beam of matter that travels at high velocities and where a large-scale magnetic field is mainly responsible for the collimation of this jet. And so with collimation, I mean that the mass doesn't flow in all directions, but only at a certain few directions. And jets are present or are launched from systems where a compact object is accreting matter in an accretion disk. And this compact object can be many things. It can be a black hole, it can be a neutron star, or it can even be a main sequence star. So these jets might appear to be something of exotic nature, but in fact they're quite common in our universe. So these jets are observed on different energy scales and size scales. The most powerful and energetic jets are found to be launched from the centers of galaxies. So these are launched by supermassive black holes, such as here. Then on smaller scales, we also have jets that are launched by neutron stars, impulse stars. But also when stars are forming, such as this system, they can create these jets. And not only when stars are being formed, also when they die, they can create jets, which is the case, for example, here. So this can happen in protoplanetary nebulae and planetary nebulae. Now, if we look at planetary nebulae, we always see these nice pictures. Now, jets are not always present in these planetary nebulae, but when they are present, they are very important for the eventual shape of these nebulae. So they really are shaping agents of these nebulae. Now, unfortunately, those inner regions of planetary nebulae are very obscured. So it's very difficult to observe those inner regions. As I mentioned, I'm looking at jets in post-asymptotic giant branch binaries, and that's the phase that comes before the planetary nebula phase. So maybe by observing these post-HB systems, we can also gain some information about jets in these planetary nebulae. Now, I wish that I could show you these pretty images for jets in post-HB systems, but unfortunately, these jets are too small and too far away, so we do not see them. So we don't have a nice catalog of these jet images. But so how then do we observe these jets in post-HB systems? Well, we see them in the spectral lines. So when we observe these post-HB binaries and we look at certain hydrogen lines, we see an interesting periodic variation that happens. So these lines change from a double-peaked emission with a central absorption to a more extended blue-shifted absorption feature. We can also represent that in this dynamic spectrum. So here we have on the x-axis radial velocity, which corresponds to the wavelength, and orbital phase. So that indicates which phase you are in the orbit from 0 to 1. And then the color is an indication for the amount of flux received. Now, if you would take a slice at orbital phase 0, that would correspond with a spectrum taken at this phase, where the post-HB star is closest to us, and the jets and the companion are in the back. And that's when we observe that double-peaked emission feature. At orbital phase 0.5, the two have swapped positions, and then we observe that absorption feature. So this absorption can be explained by absorption of the light from the post-HB star by the jets. So here you see this post-HB system, a simple example, where we have the post-HB star, the jets, and the companion. And so when we are observing this system from here, where my pointer is, we are looking directly at the post-HB star with the jets and the companion in the back. And that's when we observe this double-peaked emission feature. Now, these two stars are orbiting, so eventually our line of sight to that post-HB star will go through the jets, as is indicated here. So this means that the light from the post-HB star will be scattered or will be absorbed by the hydrogen atoms in the jet, which travel at high velocities. And that creates this absorption feature. So we have collected the spectra of about 60 of these post-stage B systems, and we see this jet feature in about 50% of them. So that shows that these jets are actually pretty common in post-stage B binary systems. And not just that, they also appear to be very diverse. If you look at these dynamic spectra, all of them are unique. So now there are quite a lot of questions about these jets and these spectra. So first, what is the nature of these jets and what is their actual launching mechanism? Then can we determine the structure of these jets, because we only have those spectra, we don't have actual images of them. And how much mass is ejected by these jets, and what does that tell us about the accretion in that accretion disk? And what is the source that feeds that accretion disk? Is it the post-stage B star or the circumbinary disk? And finally, is there a link between any of the properties in these systems? So in my thesis, I address these questions, and I did this in 4 main parts, which will also be the next 4 parts of the presentation. So first, I created a spatial kinematic model with which we can determine the structure of these jets. Then I created a radiative transfer model in order to determine how much mass is lost by the jets. And with that, we will investigate the source that feeds that accretion disk. And we'll end with a correlation study where we'll try to find links between the different properties. So first, let's go into the spatial kinematic model of the jet. So what we have is the observations. So we see the jet feature in the hydrogen lines, so mainly the Balmer lines. And what I did first is I created a model of the jet. So in this model, we have the post-stage B star. We have the jet itself with a certain jet angle, jet velocity structure, and jet density structure, and also a jet tilt. So the jet can be tilted with respect to the orbital axis of the binary. And if we then zoom in to those innermost regions, you can see that there are 3 possible jet launching mechanisms. The first one being a stellar jet, where the mass is first accreted via the accretion disk, but then launched above and below the polar direction of the star. The second jet launching mechanism is in fact a disk wind, where the matter is launched above and below the midplane of that accretion disk. And the third one is an X-wind, which is similar in nature to the disk winds, but where the material is launched from that innermost disk region. So now we have a model for the jets. What I did next is I used this jet model in order to recreate the observations, so recreate the spectra. So we recreate the spectra, we then fit the spectra to the observations using a Markov chain Monte Carlo fitting routine. Doing that, we can find the best fitting jet parameters, so we can get the spatial kinematic structure of the jet, which means those opening angles, those velocities, and those scaled density structure. So this works as follows. We start off with an initial background spectrum with no jet absorption at all, and we give that to the model. We then let the model select certain jet parameters, such as angles and velocities, and from that model, we will then calculate how much absorption will be present. So we calculate absorption on this spectrum, which gives us this synthetic or recreated spectrum. And we then fit this to the observations using an MCMC fitting routine to get our best fitting parameters. So we've applied this technique to 18 of these objects. And as you can see, the model does an amazing job in recreating the spectra. So each time you have here on the left, the observations, and on the right, the model, or the modeled spectra. So if you look at 89 Her, for example, that jet absorption feature is always present throughout the whole orbital phase. And the model nicely reproduces this. This is also the case for BD 46442. Here we have only a small jet absorption feature, And also that is nicely reproduced. But also these more unusual shapes can be recreated by the model. So this shows that the model is really successful in reproducing the whole diversity of these absorption features, but also that we can isolate the most important jet and binary components. For example, if you look at 89 Her, so here we have on the left each time a geometrical representation of the system that is created by the model. So that absorption was always present in 89 Her, and the model predicts that with our viewing angle being almost top on. So this is the post-HB star, this is a companion star, the location of the companion star, and then this is the jet, where the color indicates the density of the jet. And this line indicates our viewing angle, so we are always looking at the system almost top on. So even when these two stars have swapped position, we will still be looking through the jet, and that absorption will always be there. This is not the case for BD 46442, where we only have a small period in time where we see that absorption, and that is predicted by the model with a larger viewing angle, or we're looking at the system more edge on. So when these two stars have swapped position, we will no longer be looking through the jet. Now, if we look at all of our results, we find that these jets are in fact very wide. So they're not very collimated, they are rather wide. And they have outflow velocities larger than 150 kilometers per second, but also smaller than 1,000 kilometers per second. And this is a strong indication that this companion is a main sequence star, because the outflow velocity is always on the order of the escape velocity of the jet launching object. So in this case, that must be a main sequence star. If that object was a white dwarf, for example, we would expect outflow velocities around 5,000 kilometers per second. And then we also find that many of these jets have quite a significant tilt. And this can be explained by one or two things. This could be explained by a jet precession, so where the jet has a precessing motion. So jet precession is pretty common. It's observed in jets that are launched by protoplanetary nebulae, but it's also something that's predicted by simulations of jets that are launched from binary systems. Alternatively, this tilt could be explained by a jet deflection, where the jet is deflected due to the orbital motion of the binary. I'll come back to this at the end of the talk. And then, as I mentioned earlier, we have, or I assume, three possible jet launching mechanisms: the stellar jet, the disk wind, and the X-wind. Quite often we find that the stellar jet or the X-wind give the best fitting solution, but we cannot always differentiate between these three jet launching mechanisms. And the main reason for this is that we are probing the jet at a relatively high region. So since we are probing it further away from the jet launching region, it becomes more difficult to determine the actual jet launching mechanism. So now the second part, the radiative transfer model. So this radiative transfer model is similar to the spatial kinematic model, but it has a few extra additions. So in this model, we again, if we have the post-HB star here, in this model, you will see when the light shines through the jets. We then divide that ray up in a certain number of grid points. And then for each grid point, we calculate the local density, velocity, and temperature. So we start with the first grid point, determine where in wavelength we would get the absorption. We calculate the absorption feature, and we then iterate over all of these grid points to get this full absorption line. So as I said, in this radiative transfer model, we have a few additions. And that main addition is that we now calculate the level populations of the excited states of hydrogen. And the reason why we do this is because these level populations will depend on the jet temperature and jet density. So we have two extra parameters that we can find. Now, the way that that these level populations depend on temperature or density. It's shown here. So here you have temperature and the fraction of hydrogen in each state, with the full red being hydrogen in the ground state. These dashed lines is hydrogen in the excited states, and the blue is ionized hydrogen. So as you can see, with increasing temperatures, these fractions will change, and so will the ratios between them. So now I have this radiative transfer model with 2 extra parameters. Why not just use that one? Well, this radiative transfer model is very computationally heavy. So what we do instead is we use the results from that spatial kinematic model and use that as inputs to create a new jet model and give that to the radiative transfer codes. So now we only have 2 parameters to fit, jet density and jet temperature. And once we have all of this, we can determine how much mass is being lost by the jets, but also how much mass will be accreted in that accretion disk. So with this radiative transfer model, I will fit 4 Balmer lines, H alpha, H beta, H gamma, and H delta. And what I fit is the equivalent width, which can be used as a proxy for the amount of absorption. So here, example, if we look at H alpha, we have orbital phase and equivalent width. And so the equivalent width will peak at orbital phase 0.5, which can be seen here as well in this spectrum of H alpha, where the absorption peaks at 0.5. As you can see in these spectra, that the absorption is strongest in H alpha, and then weakens into H beta, H gamma, and H delta. And this also happens with those equivalent widths, which is strongest in H alpha, then H beta, H gamma, and H delta. So by fitting these equivalent widths, we can find jet density and temperature. So we've done this, and then we combine all of those results to determine how much mass is being lost by those jets. So here you have the companion with a smaller accretion disk in that jet. And we find that on average, the jets have a mass loss rate of about 10 to the minus 7 solar masses per year. But they do have a large range. They range from 10 to the minus 9 to 10 to the minus 4 solar masses per year in some cases. But now from this, we can also estimate how much mass is accreted via that accretion disk. So empirically, we can assume that about 10 to 30% of the mass will be ejected by the jet. So if we then work backwards, we can find or estimate how much mass is accreted. We found, on average, a mass accretion rate of about 10 to the minus 6 solar masses per year. Now, these results are important for the next part, which is finding the source that feeds that accretion. So as I mentioned earlier, there are 2 possible sources that could feed that accretion disk, either the post-HB star via mass transfer of that stellar wind, or the circumbinary disk via reaccretion. So in order to determine which one of the 2 is correct, or if both of them are correct, we compare a possible or an estimated mass transfer rate from those 2 sources, which are plotted on the y-axis, with the jet mass loss rate that we calculated. So in blue, we have the mass transfer rates from the circumbinary disk, and in red, mass transfer rates from the post-HB star. Now, this one line, indicates that all mass that is accreted will be ejected via the jets. A value of 0.1 indicates that 10% of the mass that is being accreted will eventually be ejected, and everything below this line would indicate that more mass is ejected than the amount of mass that is accreted, which is not physical, of course. So ideally, you want these data points to fall in this region. Now, as you can see, from this, the circumbinary disk is more likely to be the dominant source that provides the mass to that accretion disk. So this does not mean that the post-HB star doesn't provide any mass at all to the companion, but it means that the mass transfer rate from the post-stage B star is not high enough to sustain that eventual jet creation. But it's important to note that we don't have a full picture yet. So for these two objects, for example, we get very high jet mass loss rates. And so that eventual jet mass loss cannot be explained by either component. So that could mean that our jet mass loss rates that we estimate are too high. So we need to work on this. Need to do more research on this, improve our model. And that brings us to the final part, the correlation study. So here, we try to look for links between all of the jet binary and disk properties. So we do this by calculating correlations between a whole bunch of parameters. So in this correlation matrix, you see that red indicates a positive correlation between two parameters. Blue indicates a negative correlation between two parameters. And gray indicates no correlation at all. So we are focused here on correlations with mass accretion. So these. Let's first look at this one, a correlation between mass accretion rate and disk luminosity. So this is the luminosity of the circumbinary disk, which can be used as a proxy for the disk mass. And those two are positively correlated. Then we have two negative correlations, the one with effective temperature of the post-stage B star and the depletion pattern on the post-stage B star. So with depletion, we can determine how much mass has already been accumulated from that circumbinary disk. The higher that depletion pattern, the more mass, or the stronger, the more mass has been accumulated from the circumbinary disk. And these two are negatively correlated with mass accretion. Now, this could be explained by a decreasing reaccretion rate from the circumbinary disk to the two stars. So for example, if the temperature of the star will rise over time, but so will that depletion pattern, because we are accumulating more mass on that post-stage B star. Now, meanwhile, the mass of that circumbinary disk will be reaccreted, so that mass will drop over time. And the reaccretion rate is dependent on how much mass is available in that circumbinary disk, so also this will drop over time. So this could explain these correlations, but we do have to say that the correlations are not strong. We've tested the significance of them, and they do have quite a high uncertainty. So we need to study this further in order to determine the size of links between all of these properties. So now to come back to those important questions I raised, can we determine the complete structure of these jets? Well, yes. Shown with the spatial kinematic model that we have all the physical parameters in order to explain that whole diversity. And we can also isolate all of those most important jet components. Then how much mass is lost and accreted? Well, from the radiative transfer model, we find that the mass loss rates in the jet are rather high, so are the mass accretion rates. But more importantly, from this, we can get information about the source that feeds that accretion disk. And we find that the circumbinary disk is most likely the dominant source that feeds that accretion disk. And then are there links between all of these properties? Well, the correlations exist, but they are not strong, so we need to continue to work on this. Now, you might have noticed that I left out that first question, which was, can we determine the jet launching mechanism? Well, I've shown that it was pretty difficult to determine the actual jet launching mechanism. So this is something that is part for future work. So in order to actually determine that jet launching mechanism, we could do several things. But the main thing that we could do is improve upon our jet model. So we could include a jet rotation, because jet rotation is strongly linked with the jet launching mechanism. Then secondly, what I haven't mentioned is that in my model, I assumed the temperature of this jet to be constant. So we have an isothermal jet, which is a good first approximation, but not very realistic. So in future modeling, we can also include that temperature gradient. And as I mentioned, the jet is quite often tilted. That jet deflection, where the jet is deflected because of the orbital motion, is also not included in the model yet. So that's also something that we could do. But then instead of just improving our jet model, we can also use state-of-the-art 3D radiative transfer codes that already exist. And we can use our results as input for these codes. And then we can also model other components, such as that smaller accretion disk or those accretion streams. Or who knows, maybe even an accretion disk around the post-HB star. And then finally, we want to explore these systems in other wavelength regimes, such as the UV or in X-rays. This could give us more information about the jet's launching mechanisms or the disk itself. Thank you for your attention.
So now we turn to the questions, and we will organize it by starting with our international guests, then we turn to the local colleagues of KU Leuven, and the promoters get the final questions from the exam committee. And as it is a public defense, afterwards you as a public can ask questions, and for the people that follow online, I guess they can use the chat. And Glenn will take care of that. Is that right? So in the end, I will allow you to ask questions, but I like to start with our international guests. And as a first one, I would like to hand the floor to Professor Jonathan Ferreira. Please, Professor Ferreira.
Okay. Hi, Dylan.
Hi.
Sorry. The sound is a bit weird here. I would like to congratulate you. It was a fantastic presentation, very clear and very concise. It was really, really good.
Thank you.
And I also wanted to stress that your results are mind-bogglingly, really, I like them very much. It's a major breakthrough in the field, and I think the way you presented them and were very convincing. Of course, there are many things, as you said, to do, but it's really opening a new field of research. So it's really good. It's a new kind of systems. It's a bit like the tidal disruption events where suddenly you see accretion and ejection going on, and it allows in the systems you have to focus maybe on the way magnetic fields are generated, for instance, because as you said initially, you need to have large scale magnetic fields to collimate your jets, and that raises the question how they are coming, and is it coming from the star? Is it being advected along with the flow from the second binary? It's a mystery, right? And your kinematics that you are probing will probably provide some, better constraints. So I have still some questions. I already asked you a lot of them. I still have some questions. I was wondering, could you discriminate between, let's say, the opening angle of your jet and from the radial extent in your disk?
And the radial extent of?
Yeah, which is if you have out of the three, two models are coming from the tiny region. There's still a wind, it's coming from the star, and the X wind, which is coming really close to the star. And the disk wind is coming from a broader region. And would it be, do you have a degeneracy between, let's say, the radial extent and more collimated outflow, for instance?
I think that there are quite a lot of components that are affecting it. So not just that, but also the size of the post-HB star, which is also a free parameter. If you have a larger post-HB star and you increase that jet's launching region, you can also get an interplay between those two parameters. But then also that launching region of that circumcompanion disk is quite often not that large. So the extent of that region, it doesn't really give that much variation. And there are a lot of parameters that are entangled with each other. So
So that goes back to maybe to another question. You did not present this, but it was in your thesis. Is the discrepancy there is between the luminosity you obtain and the Gaia observations.
Yeah.
You remember that?
Yes.
And so that might maybe provide you some constraint on what you said. No.
Yeah. Yes. When it comes to the size of the post-HB star, definitely.
Exactly. Yeah. Exactly. So that might be something that you could introduce back to your model.
Yeah, ideally, we would already have perfect Gaia distances, so we could determine that post-HB radius more accurately.
And I have a final question. Is that you said there is absolutely no, well, the luminosity from the companion is too small, but is there no way, no UV or X-rays that could try to probe the innermost regions around, or the accretion shock or anything that goes with the second star, the companion stars?
I think in that sense, yes. So yesterday a paper was released about one of these systems that I looked at as well, where they found X-ray emission. So that must be most likely X-ray emission from the innermost region, maybe shocked region. So emission from the star itself would be difficult, I guess, but definitely from the vicinity around that companion, I would expect that we would be able to observe something. And also we observe in interferometry we get a little bit of emission from the location of that companion, which could be that accretion disk, for example. Yeah.
Okay. Well, I think I'm done. Thank you very much, and again, congratulations for the work you have done.
Yeah.
Thank you very much, Professor Ferreira. Now we turn to Professor Bollen from ESO in Germany.
Hello, good morning, Dylan.
Good morning.
Thank you very much for a wonderful presentation, and congratulations also on your PhD, which is very nice. So just to come back to one of the things you said at the very beginning of your presentation, you said that you see jets in 50% of post-HEB stars.
Yeah.
So would you have an idea why some post-HEB adjusts and some don't?
Two reasons. I believe that some of them are actually single stars, if I'm correct. And for others, we would expect, for example, that they don't have a jet anymore. So in several of these systems, we didn't find a jet, but we also didn't find a circumbinary disk. So that could mean two things: either there never was a circumbinary disk, or the circumbinary disk is already too dissipated, and so it can't provide enough mass anymore to create a jet. Yeah.
I see. Okay, yeah. And how many of those would be then single?
Oh, I'm not sure.
In proportion, I mean, just because, I mean, are there more single post-HEB or more binary post-HEB? To know, were you looking at the majority of the post-HEBs, or were you looking at the very little subset, which is interesting for some things, but not necessarily for the whole stellar evolution picture?
I think we were looking at the whole sample that we could observe. Yeah, and out of those, then 50% were creating jets.
Okay, thanks. And so you have been able, I mean, through all your very sophisticated technique, to really characterize the system. I mean, you have the inclination, and because you have the orbit, you can also then determine the companion mass.
Yeah.
And also from the jet velocity, you know that it's likely a main sequence star. So you have the masses of those, and so does it mean that you have also then the initial mass ratio of those systems, or did you compute them? And can this then be used to provide some constraints on the common envelope mechanism?
I don't have them, but I assume that we can use this information to eventually do a population analysis to see which of these systems can result in what. But I haven't done that analysis myself.
Okay, this is good. You have to leave some work for the colleagues. Thanks. So, and as you also mentioned, the post-HGB star, they will evolve. So do we really know if they will become a planetary nebula? I mean, do we have any hint of that?
Yeah, so let's say that these, if they become a planetary nebula, they will be too far away from us or too small to be observable. So especially if all of that mass is still in that circumbinary disk, those circumbinary disks are extremely small if you compare them, for example, with the planetary nebulae that we see. So most systems are just too far away to be observable by us as a planetary nebulae.
Okay, thank you. Well, that's it for me. So thank you again and congratulations.
Thank you.
Thank you, Professor Botta. Turn to the local colleagues, and I would like to hand the floor to Professor Sundqvist.
Yes, thanks, Philip. I hope people on StreamYard can also hear me.
Yeah. So
Yes.
there's a micro.
Oh, there is
There's
a
a
mic. Okay, yeah. Oh, yes. Congratulations.
Thank you.
I also echo the other ones, and that you have a really, really good PhD thesis here. And also, the presentation today was remarkably clear, I must say. So congratulations extra to that. So I wanted actually to ask today a little bit about, you mentioned both in your nice presentation and in the thesis that jets are quite ubiquitous astrophysical phenomena.
Mhm.
And you showed some beautiful pictures in a variety of systems. So could you perhaps discuss a little bit on what are similarities between the post-ADB jets that you're working on and the other jets in the other systems? And then is there something in your technique that you have developed that you think could be applicable to other types of astrophysical jets? And of course, vice versa, what have you learned from these other types of astrophysical jets in their analysis techniques and what type of observations?
So first those similarities I'll start with the differences actually. One of the main differences we find is that these jets are wide. So many very energetic jets that are launched by black holes and neutron stars, they tend to be very narrow. But in AGNs, for example, sometimes they also observe or get those wider jets. What I found as well is that these jets are actually quite similar to the young stellar objects. So my researcher quite often had to compare them with YSOs because those jets are way better. There's way more information about those than about the jets that I'm looking at. And they are pretty similar in shape and velocities and outflow momenta. So there are a lot of similarities, I think, between the jets in these post-HGB binaries and the young stellar objects. So that might indicate similar launching mechanisms. Then when it comes to techniques, I mainly use techniques, or I first looked at the YSOs and then applied those techniques to my systems. Then the main thing that I did differently was this binary system. So all of the models or all the papers that I saw were mainly focused on single stars that were creating jets. I had that extra binary component, which makes everything a lot more complex, of course. So that could be something that could be included in the young stellar object community, for example.
Very interesting. And just a very quick follow-up here, because you mentioned that your jets are quite wide, right?
Yeah.
In comparison to, say, jets from galaxy jets from active galaxies. Have you thought about why is that? I guess it has to do with some launching mechanism, or?
Mainly, launching mechanism, and I assume mainly the magnetic field as well. But then, if you compare it with many different objects, I think the stronger the magnetic field, and depending on the launching mechanism, of course, the narrower or the more collimated the jet beam will be.
Okay, thanks. And then just a very final question then. You mentioned also during your talk the time scales, that these post-ADB stars, in the lifetime of the star, it's very, very short. So I was just wondering, how is it that you can observe them at all then? Does the statistics work out? Should you actually be able to observe them? Have you thought about that?
Yeah. So the main difference with normal stars then is that they're very bright, so we can see them at further distances. So that's why we can see many, but with many, still a few. So we only see a few, but luckily they're bright enough so we can still observe them.
Okay.
Yeah.
And this also works out with the time scales, and if you correct for this brightness, do you know that?
I don't know that.
Or is it that they really perhaps are overabundant, or that the time scales are longer?
Yeah, I haven't checked those time scales myself, but I assume that it would check out.
Yeah, thanks.
Yeah.
And thank you, Professor Sundquist. And now we turn to another local colleague who is not local today. That is Professor Buksana. Yeah.
You're muted.
We don't hear you.
You're muted.
It seems like you are still muted.
I was still muted. The unmute button is quite hidden on my screen. For some reason, my window is not resizing. You know, we have only been doing that for years, so I still need to catch it. All right, thank you, Dylan. Thank you for the presentation. Thank you for the work. I think it's a masterful piece of work. So congratulations on that. Of course, I have a few questions, and the first one is triggered by basically the first definition you give in your first slide of your presentation today. What is a star? Can you repeat that definition for me?
Yeah, so that was a very simple definition, but
so then give me a correct definition.
So yeah, a star is again a large sphere of matter. So a star is there are two main actors in stars. We have gravity, which creates an inwards.
Too complicated. Give me a definition of star.
A star is a large ball of matter, which is being kept together by gravity, and which is so that inwards collapse is prevented by something that pushes it outwards, and that is sustained by those fusion reactions in the core.
Good, thank you. I have all the ingredients of what a star is that prevent us to get confused with a planet or get confused with a black hole. So that's perfect. All right, and the other question, again on your introduction, you mentioned that the first nuclear reaction that happened is hydrogen burning.
Yeah.
Are you confirming this? What is the first reaction that occurs in the trigger that is triggered when the star is contracting, or protostar is contracting?
Oh, that's a tricky one.
Well, I think it's in the course of Hans in the first bachelor.
Yeah, it's true. But that was 10 years ago.
And that was not Hans.
Yeah, I'm not 100% sure. So we're gonna.
You heard about deuterium?
Yes. Yeah.
All right. All right. I have two questions for you, and one of them I have actually asked it in the past. One of the things that you find, I think, is beautiful is the fact that your model is able to reproduce every pieces of line profile that you have in your data set.
Mm-hmm.
Does that mean that your model is actually perfect, or does that mean that you have actually too many free parameters? That question.
It could be one or the other. I think the model is very free, so there are a lot of parameters, but I do think that so overfitting could be a problem, but I do think that we get the most important things out of the model.
And so, what basically is allowing you to basically argue that your model is capturing the physics of the process?
In that sense, we can compare it with just looking at the results itself. So out of that geometry, for example, we then use that radiative transfer code to get the mass loss rates, and they are very close to what we would expect for mass loss in the circumbinary, from mass accretion from the circumbinary disk, for example. So if that would be completely off, that would have been a strong indication that the model is overfitting.
So the fact that the results of your model is providing you something that you expect is a strong argument that your model is working?
Yeah, not necessarily. Yeah. We'll say the fact that it's not sure what to say.
Continue thinking about it. I mean, I think it's fine. You've done all what you can do, and the results are beautiful. But keep in mind that it's not because the model is working that you actually have the correct answer, and we actually have the problem currently in our group. Fortunately, that was before publication, so we are not in trouble yet. But that's a point of attention when you fit a model. It's not because the fit is good that the model is correct.
Yeah, sure.
I have another question, which I basically noticed during your presentation when you showed this correlation matrix.
Yeah.
Something I did not notice is that you have a strong correlation, a strong anti-correlation between the velocity of the jet and the luminosity.
Yes.
And I was expecting that those would be more correlated, not anti-correlated. Yes. Can you walk me through the physics of that?
So that's indeed something rather unexpected. So important there as well is that luminosity is the luminosity of the PhD star and not the luminosity of the companion star.
Yeah, of course.
So you have the velocity of the jet launched by the companion that is negatively correlated with the PhD star, I assume. So the physics of that I can't tell because that is very unexpected.
So the first point indeed is that the jet is launched by the other star, not the star that for which you have the luminosity in the grid.
Yeah.
But then that means that lower luminosity AGBs are smaller.
Smaller, yeah.
Okay. I don't have the physics yet.
No.
For more research then.
Yeah, indeed.
Thank you. I think I will hand over the floor to the chairperson, and then Nick, you can do whatever with it.
Okay. Thank you, Professor Sama. So then we have all the international and the external jury members, and then we keep with the promoters. So I would like to start with the Australian promoters. Professor Ursula, do you want to ask some more questions?
No, I won't ask your question, Dylan. You and I talked enough times. I just wanted to say the presentation was absolutely spot on. And I hope our non-technical members of the public enjoyed it as much as I did. It's always great to see the results. And I just, you just open more avenues and more questions. And Ari knows very well my interest is in figuring out how you even make the systems in the first place. And I think, although you might say of your thesis that you haven't got all the answers, and we know we haven't, right? All those accretion rates are far too large. It's really hard to justify. There's lots and lots of open questions.
Yeah.
But the thing is that these systems, as they will be studied further in the future, are the first tangible way to get answers. Before, we just make a lot of suppositions, and we work on very little data, but these are very real. And the jets are very, you do measure those angles because the geometric models, even when you haven't added a lot of ingredients, really give you something.
Yeah.
So thank you, and really congratulations.
Thank you.
Thank you, Professor De Marco. Then Dr. Kamat.
Yes. Hi, Dylan. Congratulations on that fantastic talk. I thought it was really relatable on many levels. You started off at exactly where one needs to start off by simplistically telling us what a star is, and then effortlessly taking that on to binary systems that have these jets. So really well done. So my question for you is, when are you taking up your postdoc position to continue your research?
No
we
idea.
we need you to work more on these jets. I mean, there are so many important questions, and so yeah, when are you coming back to Australia and taking on a fellowship? Hopefully, you get one.
Coming back hopefully ASAP.
Well done. We're waiting for you. Well done.
Thank you.
Okay, thank you, Dr. Kamat. Then the final.
No, I don't have questions for the moment.
No, no. And then the
Ask many questions before.
I hope so.
That's true.
And then because it's a public defense, I would like to finalize by asking you as public whether there are some questions you want to ask to Dylan today. Yes, please.
Hey, Dylan, very nice talk. Very well explained. I have a question about the first part, the determining the shapes of your jets. Did you sometimes have multiple solutions that were vastly different jets that would explain the same spectrum?
Yeah. Yeah, that was mainly the case in the beginning when I started modeling this. It did occur sometimes that I had different possible solutions that could get the same fit. But using the technique in MCMC, you always go to the best fitting one. You hopefully always go to the best fitting one. And secondly, those three jet launching mechanisms, they were difficult to distinguish. So quite often, or almost always, they would all three give a similar overall shape as well. So sometimes you do get different fits that are possible, but it always goes to the best fitting one is clearly the best fitting one. Yeah.
Okay, thank you. More questions from the public? Not here. Okay, please.
Thank you, Dylan. Congratulations. I noticed that everything you spoke about was spectroscopy.
Yeah.
Is there anything from photometry that you could use to constrain your models?
There's information we can get from photometry, definitely. Information about these systems. For example, from photometry, we know that there are no ellipsoidal variations from the post-HB star, which gives us information about the Rochelot filling factor. So the star's not filling its Rochelot, which gives us information about the possible mass transfer from a post-HB star. And we can rule out Rochelot overflow, for example. But yeah, that's hopefully that we can also detect something from those jets itself. So with photometry, I don't think pretty sure we don't have anything about the jets or that accretion disk itself. But therefore, when we look at X-rays, for example, or something, we might get more information. Yeah.
Okay. More questions from the public here? If not, I turn to Len to ask whether there are chat questions.
If no questions.
No questions, Len. Okay. So then the committee will resign and we will come back after the deliberation. Okay, so ladies and gentlemen, dear colleagues, I will now proclaim the result of the deliberation by the exam committee appointed for the doctoral degree in science, astronomy, and astrophysics. Mr. Dylan Bollen has presented to the faculty his PhD thesis on the topic of jet creation in post-asymptotic giant branch binaries. This was in partial fulfillment of the requirements for the PhD in science, astronomy, and astrophysics, and he has defended his thesis in a public session before the exam committee. The examination committee has determined that all requirements concerning the granting of a doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of KU Leuven, I confer upon Mr. Dylan Bollen the degree of Doctor in Science, Astronomy, and Astrophysics. Congratulations, Dr. Bollen, and I close the session. Now the official part is closed, but I would like to hand over the word to the promoter, I guess. They will share who is telling what.
Als een van de promotors is het natuurlijk een eer om u als eerste met uw titel aan te spreken, dus beste Dr. Dylan. Dear Dr. Dylan. In fact, it's a double degree. So it is a double degree with Macquarie University. So you could even say Dr. Doctor or double Dr. Dylan, which is also a nice alliteration. These are likely not the circumstances that you have had imagined for a PhD defense. But anyway, we will have to, we still can celebrate, although the toasting of the celebration will be done at a better occasion where we actually can do it. And there are many reasons to celebrate. A particular aspect is that we celebrate at both hemispheres. So it's like the aurora. You have a PhD borealis and a PhD australis. In mechanics, there is a circumstance that the difference between the begin status and the end status is independent of the path. So it's called with conservative force. I think a PhD is not like that. I think the path is really making the PhD. And you, I think, is a living, or a living proof of that. Yeah, so you started your PhD on the borealis side. And it was a very, very good timing for many reasons. First, of course, you had a head start with your master thesis because that was also on those similar systems. And our universities, just at the moment of your graduation, I think they announced that they had a common agreement to foster co-tutels. And so I think you're also the first co-tutel in this agreement. And so it's another reason to celebrate. So with Ursula and Devika, we quickly set up a co-tutel agreement. It was not as quickly as possible, so there was some administration, but okay, we set up and off you went. The first year at the time, so the first year was here at the borealis side, and then you went to the australis side. And we will hear about that in a minute when Devika takes over. I was lucky enough to come to visit you, and I remember the moment we met because you also started to study mechanics in your free time. So you did weightlifting, and I was quite impressed. And at that time, it was a long time ago, we still could shake hands. So do you remember the time that shaking hands was still possible? We did so, I did so, and I was lucky that he did not test his muscle strength on my But you also grew there as a researcher. The Australis part of your PhD, you grew as a researcher, and we'll hear about that moment, in fact, any minute. So the second part of your borealis side, back to the other hemisphere, was quite impressive to see because you saw all the puzzles are falling together and in the right order. So it was really the puzzle going to the nice end, and I think that was a very rewarding period. I think you will agree with me that the period here back was really where you took off as a PhD researcher, and I think we heard it during the nice presentation, but also during the defense, that it was a really impressive piece of work. So, Doctor, congratulations. What is coming now, career-wise, is a bit veiled still. But I think with a PhD Australis and a PhD Borealis, I think you can go everywhere. So I want to thank also Ursula and Devika for the nice collaboration. And I hope you are just the first one in a whole series of PhD students that will profit from that Hotel agreement. And I happily give the floor to Devika to continue with the presentation.
Thank you.
Thank you, Hans. And may I say, you had very befitting metaphors. So I really liked the auroras. So, Dr. Dillon, or should I say Dr. Dillon, congratulations. I think we are all very proud of you. And I think I can safely say this on behalf of your entire supervisory panel and your thesis examiners. I'd like to take Dylan and all of you who have joined us here today on a trip down the memory lane. So Dylan started his research career with Hans and me as a master's student. Subsequently, thanks to the massive efforts of Ursula DeMarco and Hans, of course, an opportunity arose for the possibility of a co-tutel project. As many of you know, in this case, it referred to a PhD program which involved the first year to be completed in Leuven, and 2 years, almost 17,000 kilometers away at Macquarie University in Sydney, and then he would come back to Leuven again for his 4th year. Now, what struck me, and I think also Hans and Ursula at the very beginning, was that Dylan was one of the few students we had back then who put up his hand and said, I'm eager to take on this dual hemispheric PhD program. I'm happy to explore the world and travel. Now, most of us can appreciate the emotions and the hardships and the stress that comes with a 4-year PhD program in one country. But I think only a few of us can understand the difficulties of relocating internationally, not once, but twice, during a 4-year PhD time span. And Dylan, he did this with great panache. Let me quantify this for you. In addition to a remarkable thesis, which of course the examiners, as you've heard from Jonathan, have labeled it as groundbreaking, he has 4 first author papers to his name. He has successfully led a proposal for the very competitive ESO facility, and he has also contributed to teaching and tutoring duties in 2 universities. If you think that's a lot, then hold on, because there's more. Dylan spent a great deal of his time and effort working with the structure and kinematics of post-AGB binary jets, but he also spent a great deal of time working on his own structure and kinematics. And I fondly recall having several conversations on fitness regimes and protein shakes in my office. And if you think that, keeping up with physics and fitness is a lot, then Dylan took it one step earlier. He found love in Australia. He found himself a partner, Christina, to share his academic and personal life with. And of course, I wish him and Christina the very best. So a lot has been done in 4 years. And, it's quite a journey, I must say. And I absolutely commend Dylan for his academic achievements. But what makes me prouder is really the person that Dylan has evolved into. And some of the attributes I deeply appreciate is his maturity, his ability to calmly and confidently handle situations, and most importantly, his ability to take feedback very positively and benefit from it. Another skill that he effortlessly displayed, a very difficult one, is managing a team. Now, many of the PhD students listening to me right now, I think you might agree with me that managing a supervisor is difficult. In Dylan's case, he had to manage 3 supervisors, okay? So having 1 supervisor is tough, but having 3 is a challenge. And I think many students can relate to this, because imagine getting feedback on your paper not from one supervisor, but 3 supervisors. So you go through that process, and then of course you have the referee. But Dylan seamlessly managed this, and I think importantly, he was able to capitalize on all our strengths, Hans, Ursula, and mine, and come up with great theses at the end of 4 years. Now, an example of this is a strength of Dylan's theses is really how he intermingles observations with theory. And this is really something that he's been able to achieve by kind of capitalizing on the strengths of his supervisory panel. And this is really an essential skill, both in academia and also in industry, if that's what should happen. So Dylan, well done once again. And I'm very glad to have had the opportunity to work with you and supervise you. And I'm sure that Hans and Ursula feel exactly the same way. So you finished a very important chapter of your life and you are about to enter a new one. And I believe without doubt that the institution that you will enter, be it academia or industry, they are going to be very lucky to have you to work with them. All of us, we look forward to watching your journey and supporting you in any capacity we can. And congratulations once again for the impressive PhD journey, and we wish you all the very best.
Thank you. Thank you.
I will not take any more of your time. I'll just say that I completely echo what Devika has said, and I totally agree. This is not easy. And, I see struggle of PhD students all the time, including those who have less a tricky career path and PhD with many countries and many supervisors. When you arrived, I thought you were doing great from the start. I remember when I met you I met you in France, remember, at that conference.
Yeah.
And I was really excited. You seemed just like the person who would do great. Then you arrived in Sydney and you started working really hard. And then my students arrive in Sydney, my international students don't realize that we are quite so close to so many beautiful beaches. And I don't tell them, because I have no interest in them looking at the beaches. But then you realized there was a beach, and I thought, damn, this is not going well. And then love, oh my God, this is downhill. But no, you did really well and actually grew through all your experiences, and you have a tremendous work ethics. And it's been a real pleasure and a learning journey for me as well to work with you. Well done, Dylan.
Thanks. Yeah. So now I want to thank a few people as well, of course. I think it goes without saying that I want to thank my supervisors for making all this possible. I don't know if you remember, Ursula, about 5 years ago when I sent that first email to you, asking if I could do a PhD under your supervision. So back then I did not know that you and Hans already knew each other, or already knew each other well. And I also I wasn't aware that the 2 universities were already setting up an agreement. And then it turned out at the same time, I told Devika that I contacted you, and then she told me that she's also going to Macquarie, and I didn't know about that. But so those were a lot of coincidences. But I'm very happy that they were there, because that eventually led to me being able to do this code to tell. So thank you. It's not always easy having 3 supervisors, but the 3 of you always made time for me, even when we were on completely different time zones. Like Hans, you had to wake up pretty early sometimes in order to have a meeting. Or Devika and Ursula, you quite often would already be at home, and then you still had to make time for me. But all 3 of you, are always there. And I really appreciate that a lot for all of the help and the supervision that you gave me. So thanks a lot for that. Devika, I hope I set a good example as your first PhD student.
Yeah, actually second, but yeah, absolutely. I think, absolutely, but one of my favorites.
Well,
thank you.
Normally it is a reception now,
yes.
But I do have a small memory for your PhD.
Oh, Also have something for you. So no, it's tradition for you to get a bottle of wine.
Yeah.
So I made sure it was alcoholic, but I made it myself.
Oh,
I made, I made one bottle of limoncello and one bottle of Mandarin cello.
Oh, wow, thank you. Congratulations. Normally there is a reception now, but
Fortunately.
congratulations.
Thank you.
I'll do the